welcome everybody. A very good morning from FOSSEE IT Bombay. I am Payal Mukherjee, working as Senior Project Manager at FOSSEE. Let me first introduce Mr. Chakrabarty, and then we will hand it over to him for his session. So Mr. Arnab Chakrabarty has done his MTech in Ocean Engineering and Naval Architecture from IIT Kharagpur and an MS by Research in Mechanical Engineering Thermal from IIT Madras. He has previously been an SN Bose Scholar at Texas A&M University and a VSRP Fellow at the Clean Combustion Research Group at KAUST KAUST, Saudi Arabia. He has received internship awards from the Indian Academy of Science at IISc, IIT Madras, and IIT Gandhinagar. He has been honored with the Indian National Academy of Engineering Innovative Project Award by the Department of Science and Technology, DST, of the Government of India. A prestigious accolade given to only 8 individuals nationwide and the sole recipient from IIT Madras and West Bengal. Additionally, Mr. Chakrabarty has worked as a simulation engineer at Emerson Process Management and as a fluid mechanics consultant at Analytics Plus Incorporated. He has authored 7 journal articles, 30 conference papers, and 5 book chapters. Mr. Arnab has also served as a reviewer for the esteemed journals such as Physics of Fluid Atomization and Sprays, and IMechE and conferences including FMFP, ASME, Gas Turbine India, GT India, and ASME. So we are really fortunate, we are really thankful to have Mr. Arnab today as a guest speaker in this workshop. And I hope his session will be a very useful one, very informative and effective one for all the students, faculty members, as well as the CFD professionals who have joined today. So Mr. Arnab, actually the audience is a mixed crowd. Majority of them are students, and some of them are also faculty members, and a few of them are from the CFD professional background as well. So over to you. You can start the session today.
So thank you, Pal, for the nice introduction. So so today I'll show the different sides of the droplet dynamics, which are very relevant in nature as well as in the industry. So that's why I kept the name purposefully, that the droplet dynamics across the spectrum from traditional CFD to modern molecular simulations and ML-based models. So the intention of this talk is not to show the detailed numerical simulations. Here my intention is to give you an overview that what kind of work we are doing in presently in the TCS research, as well as the state of art, what people are doing on the across the globe on this domain, and what are the possibilities, what are the scope you can work on or you can think upon. So yeah, so I myself, Arnab Chakrabarty, I'm working as a scientist in TCS Research, that is the Tata Consultancy Services Limited R&D, and here our team basically deals with different multi-phase flow problems across all domains, from the chemical processing industry, aerospace, the ocean or atmospheric sciences, the climate change, etc. So the overview of the talk will be the background. I will share basically the 3 individual case studies to give you an overview. So some of the studies, the most part of the this talk will be on CFD, and after acquiring the data, CFD data, we did some machine learning, and as you know, the CFD and all are the mesh-based methods, and finally I'll touch upon the meshless methods or the molecular level simulations of the same thing, to give you an overall idea and the differences between the CFD and molecular dynamics, and how those are useful and etc. So let's coming to the talk. The overview of the talk is will be the background. I will discuss briefly the background of each of the problem associated with the respective case studies, then the novelty and objectives, then the computational setup and validation of the model, then the modeling of the spreading parameter, that is an image processing based approach. So there are many approach. I will mostly focus on the image processing based approach. And then we did several variations. Those are the parametric studies, that is the effect of impact velocities, inclination angle, static contact angle, etc. And then the effect of non-sphericity of the droplet on its spreading, and the machine learning in droplet dynamics, and then I'll conclude. So before going into the simulations or the studies, first let us see the background. Okay, so droplet, the um, application of the droplet dynamics could be found in nature as well as industry, as I already mentioned. So in nature, in many aspects, these problems are useful. Let's say a droplet is impacting on a leaf, okay, and that droplet carries certain amount of bacterium. So upon impact, the droplet will spread, right? So it will spread the disease also. So based upon its maximum spreading, one can predict that how much the disease can spread within that residence time. It means the droplet impacts and it leaves the surface. Okay, in between this time is called the residence time or contact time, whatever. So yeah, in the other in another example, you can see during the COVID transmission, we were very obsessed with the droplet, and even though apart from COVID, there are many other disease that can be transferred or that transferred using the droplets basically, and and you don't know how they will spread. Even nowadays, the recent study shows uh, the this urinary tract infection that is very prominent in the young woman, that is also spread due to the droplet transmission in the public toilets. Okay, so that is why uh, it's dynamic, how it evolves with time when it interacts with the surface is very important to study. And further, this droplet dynamics is having application in changing the local climate. Let's say when a wave breaks in the shoreline, so it produce very fine droplets, and due to the temperature and humidity and other stuff, that those droplets gets evaporated and change the dryness fraction of that local area, and eventually that contributes to the climate change. Further, let's say when a flight is going through the cloud or going through the volcanic ashes, okay, those if it is going through the cloud droplet usually interact with the this compressor blade, and if it is a volcanic ashes, eventually sometimes the metallic droplet, the liquid molten metal droplets uh, just comes and hit the compressor blade, and is having uh, mm, several consequences, like the imbalance in the rotating machinery, like compressor and all, and then its erosion, and if that droplet is reacting with the blade material, then corrosion. Okay, so eventually it is, and rain droplet impact on the wind turbine blades. Okay, so eventually that the how the droplet interact, or how the droplet what could be the dynamics of the droplet upon impacting on several test cases, whether it is compressor blade or whether it is wind turbine blades or it is fixed surface. um, it is important to study to understand the dynamics. So every time the dynamics changes with time, and it varies case to case basis, so there is no direct correlation exist among the all cases. um, so this is the case study one. Now coming to the case study one, as I said, I will show three different case studies, and uh, you will see the differences. So this is the first case study, that is yeah. So that is the numerical simulation of post-impact dynamics of a droplet on an inclined surface. Okay. So these are the lacuna of the literature. Uh, as you can see, yeah. So it is imperative to mention that most of the studies were experimental, and most recent studies among all reported literature are up to the inclined plane 60 degrees, but we have extended our study up to 75 degrees. Okay. So it could be observed from the few numerical studies that the dynamic of the droplet changes in the tangential direction above 70 degrees, while there is no mention of the post-impact dynamics of the droplet on in the lateral dimension. It means that when the droplet is impacting on the inclined surface, eventually, although the droplet was initially was spherical, but when it spreads over the inclined surface, it is having two spreading parameter. One is along the axis or along the motion, and the motion or along the axis, that is your longitudinal, and one is the in the lateral dimension. So most of the previous studies mentioned about this longitudinal or along this axial spreading, but there is no mention in the lateral spreading dimension, because that is also important in certain applications like coating, spray drying, painting, 3D printing, etc. So we have reported we have reported the lateral dimensions also, and we try to correlate this lateral dimension with the axial dimensions. Um, all previous studies were focused mainly on the rebound and splashing regime, whereas thus there is a substantial gap in the literature for the deposition regime, which is having direct implementation in spray painting, tablet coating, 3D printing, and metal additive manufacturing. Okay. All the previous studies talked about the dynamics of the spherical droplet only. However, if the droplet is larger, uh, or or if they are a polymeric droplet, they multiple times they cannot sustain their sphericity, and they becomes non-spherical while impacting. So there is no literature available that discuss the dynamics of the non-spherical droplet upon impact. And uh, so droplet compressor blade interaction or droplet turbine blade interaction or whatever, droplet and any rotating parts, rotating machinery is a major issue which need to be addressed. And yeah, there are very few machine learning models available for predicting the droplet dynamics upon impingement. So mostly, if you see the literature, all those machine learning models are applicable for very basic test cases, like droplet is impacting on some smooth plane surface kind of stuff. But when so as you know, in the machine learning we usually give some input parameters and we expect something at output. So let's talk in a layman's term. So if you are giving some inputs, so if you are increasing the complexity of the problem, like if you are giving the inclination angle or heat transfer parameters or the rotational motion or the translational motion, whatever the input parameters, eventually it is the complexity increases to train the machine learning models. Okay. And at the same time the computational cost also increases, and the and if your data set is not adequate, eventually the convergence issues also come. There are several reasons for that. The people have started with the sample cases, but we will show you some complex one. And another thing is that uh, nowadays machine learning is evolving in all across all domains. Okay, so it is very important to consider as a very useful tool because the CFD simulations, each of the depending upon the grids and other things, the machine configuration, etc. The CFD simulations usually takes lots of times. Let's say for our case, for a single case study, uh, let's say a droplet is impacting on an inclined plane, and you are using 12 lakh grids, 12 lakh to 15 lakhs grids, and it usually takes 10 hours. So in a 8 core processor, let's say, 8 GB RAM, so it usually takes 10 hours. Okay, so eventually every day we usually runs thousands of simulations in the industry, so it is not possible so to run every time the CFD simulation. So what we do, we usually run the simulations, and whatever we have performed the simulations in the last few years. So based on those data, we try to develop the machine learning model so that they can able to predict precisely or within the specified accuracy, let's say within 80% or 90%, the actual dynamics, so that we can save a lots of time, effort, as well as the computational cost. So that's why the machine learning models are very useful nowadays for modeling these multi-phase flows or these droplet dynamics, whatever. And there are very limited numerical studies available for the dynamics of the droplet on a plane having different motions. So if you see the literature, multiple the problems associated with the droplet dynamics on the fixed surface. But once you are considering the moving surface, let's say the droplet is impacting on some unidirectionally translating motion or some vibrating motion or the rotation or the combined of any of these motions. So eventually, if you introduce the motion on the surface, the problem becomes more complicated, and eventually for these kind of problems, these droplet dynamics kind of problems, so it is uh, very important to track the triple phase contact line. Means where that when the droplet touches the surface, eventually uh, with time it will spread, right? It will spread, it will reach its maximum spreading limit, and then it will start to recede, and then it will jump off from the surface in case of rebound, and or it will splash eventually uh, if the impact velocity is very high, and if impact velocity is very low, it will deposit, it won't rebound. So eventually so in all cases, it is very important to track the triple phase contact line where the liquid droplet meets the surface, solid surface, in the air medium or whatever in the gaseous medium. So when you are introducing the motion on the surface, eventually the tracking this triple phase contact, accurately tracking this triple phase contact line becomes very important. And for that, we need to incorporate the kind of uh, we need to couple actually some other complex model. Okay, you cannot handle uh, the the things similar which are similar to the fixed surface. Okay, so in many aspects this problem are complex and useful. So all the previous studies are mostly experimental and reported at a higher Weber number, let's say above 100. But in present study, we numerically investigated the droplet dynamics at the planes at different inclination angles in a wide range of Weber number, varies between 0.01 to 200 The effect of inclination angle on the droplet dynamics has been systematically studied. Here the range has been considered for 5 degrees to 80 degrees, and the effect of static contact angle on the droplet dynamics has been systematically studied. The range of static contact angle varies between 75 degree to 156 degree. It means that for a particular liquid droplet and a particular surface, they are having a constant SCA, static contact angle. Let's say you are using the water droplet and you are using some glass surface, so eventually the static contact angle will be fixed. Let's say it is 105 degree or whatever. uh, if you change the surface, in place of glass, if you are using copper surface, okay, or some other surface, eventually that static contact angle will change. So this is the significance. So if you want to change the material, you can change the static contact angle eventually. So the effect of the droplet shape, that is the spherical or non-spherical, on the dynamics upon impacting the oblique surface over a wide range of Weber number, Reynolds number, inclination angles are investigated. So the non-spherical droplets are having special significance. I'm telling you why. Because if the droplet is small, eventually the gravity effect can be neglected. Small means we have found experimentally that if the droplet diameter, let's say, is less than uh, uh, 2.9 or 3 eventually the gravity effect is not so much. That means the bond number is very, very less than 1. So you can neglect the gravity effect, and eventually the surface tension retain its sphericity. But if the droplet size is more, uh, let's say it is 3 or 3.5 or 4 eventually you will see that when the droplet hits the surface, eventually it is not spherical, it becomes non-spherical. And this is the one thing. And second thing, if the surface is having the charges, okay, the surface content charges, eventually uh, uh, you are putting some ionic liquid droplet, eventually droplet becomes non-spherical. And another thing is, if you are using some polymeric droplet, so sometimes when it hits, it's stretched, okay. And another thing is that, let's say you are having two consecutive surfaces, like like this high power lines, in the high power lines, okay, transmission lines. So um, if a droplet hits the first line, and then when it is going to hit the second line, its shape is deformed and it is no longer spherical. So you need to allow the droplet for certain time to retain its shape. So many times this hitting time scale is much lesser than the time scale required to regain its shape. Eventually at that point of time, these droplets becomes non-spherical, okay. And these issue has been rarely addressed in the literature, so we did it here. So the tangential and the lateral spreading factors, contact time, sliding length, and leading edge and trailing edge length, regime plots of the different dynamics, time evolution of the pressure velocity contour during the different dynamics over a wide variety of parameters, like Weber number, inclination angle, static contact angle, droplet shapes we have studied. And then the different we have, as I said in my earlier slides, that we have incorporated the different machine learning models, but here I will show only one, because yeah, it is a all together different domain of studies, so you can do lots of stuff. So yeah, here I must mention the challenges in the modeling. So due to the rapid deformation on the droplet free surface, it is extremely challenging to capture those multi-scale physics. Okay, hence very fine mesh is usually required. But sometimes we have seen that if your mesh size and uh, your grid size and a number of grids is not adequate, means you are if you are not uh, if you could not able to resolve the grids where the rapid deformation is happening, eventually that changes your dynamics. Means, let's say actual dynamics is rebounding, that droplet is hitting just like a ping pong ball, and it should rebound from the surface. But if the grid convergence is not properly done, eventually you will see the splashing. Okay, so you don't know. So if you don't have any reference, you don't know eventually whether actually it is the grid converged or not. So anyway, and again, modeling the triple phase contact line, there are different algorithms to model the triple phase contact line. So that is another important task. If you cannot able to track this triple phase contact line, eventually all of your calculation will be erroneous. So you need to be very careful about that. Then the dynamics of the droplet is a complex phenomena and which depends upon the many forces acting on the droplet gas interfaces, droplet solid surface interfaces, and moreover boundary conditions plays a very vital role in this. As you know, in the CFD simulations, these boundary conditions are the game changer. So in case of either of the conditions is not properly maintained, the dynamics will eventually change. Now, the modeling of, as I mentioned, the triple phase contact line is challenging task to implement. Most of the literature reported the simulation using static contact angle modeling approach. There are certain literatures they use the dynamic contact angle modeling, and for dynamic contact angle modeling means when the droplet is spreading or it is receding and whatever, at each and every time instances the contact angle is changing, right? Because it is a fluid. So there are different models like Chrysalis model and other models for the dynamic contact angle. So you need to handle this differently. So results start to deviate from the actual one at the higher impact velocity cases where the droplet interface rapidly deforms if you are using the static contact angle models. So that's why the dynamic contact angle modeling is required. So due to the larger uncertainty in the behavior in the post-impact dynamics of the droplet, there are scarcity of the literature in the machine learning models also, as I mentioned earlier. Now coming to the computational domain. So as you can see, yeah, this is our computational domain. So in X, Y, and Z axis, it is the box, the size of the box, the simulation box is 30 mm cross 5 mm cross 6 mm. Eventually, the diameter of the spreading, the spherical droplet is 2 mm. Okay. So impact velocity, initial impact velocity is 1.5 meter per second. Angle of inclination is 80 degree. The droplet primary phase is water and the secondary phase is air. The wall bounded the wall boundary condition are used at the surface and the wall of the domain. So now once you made the simulation, so we have used the Chrysalis model for the dynamic contact angle modeling that I did not mention explicitly. Then once the simulations are done, you need to what we did, we did the animation and then we uh, 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 did the image processing. So these are the different stage of the image processing. From the animation, you need to convert from the video to uh, the image frames, and from the RGB image you need to convert to the gray image, and then to the binary image with suitable intensity thresholding. And for that, if you if you want to do that uh, 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 automatically, mostly people use Ostrow's algorithm, and sometimes that algorithm doesn't work well, so we need to do it manually, and for that we need to check the image processing uncertainty also. And what we usually track the extreme points of the droplet where it meets the solid surface. Okay, so eventually you can calculate the axial spreading and the lateral spreading. Okay, you can calculate the depression of the vertex point of the droplet also, and that shows how yeah how it height also varies. So eventually, if you can able to calculate the spreading diameter, eventually that is proportional, inversely proportional to the height of the droplet, because anyways it need to satisfy the conservation of mass. Okay, so yeah, so this is the machine learning algorithm. So we use several things: the decision tree, AdaBoost, and the SVM, the supporting vector machines, and and other. There are lots of algorithms. There is a detailed study. So once the paper is under review, so I cannot reveal much. So once that is come, you can go through it. So anyways, so here my intention was to show how this algorithm works. Okay, so that's why I have included only one AdaBoost algorithm, so you can see the flowchart of this algorithm. That is, first you start, and then you give your input parameters. Okay, so here your input parameters are and y is the corresponding level. So your input parameters are, let's say, inclination angle, impact velocity, Weber number, Reynolds number, etc., what I have listed. And then you initialize the weights. As you know, you need to give some initial weight, and then the sample data set according to the weight gives the data set in the decision stamp. So the decision stamp will give you the prediction as, yeah, here we have taken the parameter as hfx. Okay, and then if your t is less than capital T, then compute the weight at uh, the next interactions, and eventually you will get the diameter, and you compare it. If it matches, then yeah, the loop will go on, and if it doesn't matches, so you just calculate these parameters and the predict level for the xis, and then it ends. So yeah, and during the simulation, so this slide should come before the CFD simulations. If you see the model parameters, we have used the VOF, that is the volume of fluid method. The primary phase is water, the secondary phase is air, and the viscous model is laminar. Pressure velocity coupling, we have used the simple. The pressure discretization is presto, and the surface reconstructions is georeconstruct. The time step is 10 to the power minus 4 seconds, and the total number of time step is 150 to 400 depending upon the problems. If the impact velocity is higher, eventually you need more time step to converge, and if it is if the impact velocity is less, eventually your number of times should be less. So the physical time scale we have simulated up to 15 milliseconds. So why it is that? So within 15 milliseconds we have observed we can accommodate all the dynamics, and we have varied the static contact angle between 45 degree to 156 degree. Now, there are certain assumptions in the simulations that there is no heat transfer into the system. That is the isothermal assumptions. The droplet volume is constant, viscosity of the liquid, and the liquid is incompressible, and outer air is compressible. So yeah, eventually you can see this is the overall geometry. So overall dynamics. What is happening? The leading and trailing edge length. Why are they important, and how to calculate? So as I already mentioned that we have used 0.12 mesh size was found to be optimum for 12 black grid elements, and the simple scheme is used over piezo due to the simplicity and the computationally less expensive. And yeah, so the first one is the side view, and the and top view is also shown. So as I said, there are two different diameters. One is the tangential, one is the lateral. So tangential means along the axis. That is also called the axial diameter, axial spreading parameter, and the another one is the lateral one. So yeah, so these are, you can see the comparison of schemes and the grid convergence. So yeah, the first one is the grid convergence. So you can see once we finalize the simple over piezo, we run the different the same simulations with different grid size, and we compared with the Kwan et al. That is published in Causeway. and you can see the grid convergence. We have calculated the length. This is the sliding length of the droplet, and if you see the comparison of schemes, so there is as such no significant difference between simple and piezo. So simple is much simpler, that's why we use the simple. Yeah, so now these are the quality validation plots. Okay, yeah, so these are the validation plots. As you can see, the first one is from Guan et al. Based on what we did all the validations, and the next one is the experiment. The first one is the simulations, the VOF simulations. The next one is the experiments by Sikalo et al. And the third one is Sahu et al. For the we have used this is the for the experimental validation. So anyways, so coming to the first figure, probably yeah, yeah, so this is the one et al, this is the Sikalo et al, and this is the our simulations at different the time stamping. Okay, so yeah, and yeah, this is for the inclination angle 80°. These are the visualization images and for these specific parameters, and these are the experimental validation with Sahu et al, and we have calculated the error that is always less than 5%. Now, yeah, now what we are calculating the spreading parameter, that is the instantaneous diameter, because every time when it is spreading or whatever, so every time you can see that the diameter is changing, and we are non-dimensionalizing that using the initial diameter. So eventually it is the ratio between the instantaneous diameter to the initial diameter. So that is called the spreading parameter. So yeah, so these are a few animations you can see for different Weber numbers at different inclination angles. So this is the your alpha at 30°. That is the inclination angle 30°. You can see when the Weber number is less, eventually you can see the depositions is there at 0.05. So droplet is not coming out of the is not rebounding from the surface. It is a pure case of deposition. So this deposition is very important in the spray coating, tablet coating, 3D printing, etc., where it is undesirable to if the rebound or the splashing occurs. So when we increase the Weber number to 40, eventually you can see the rebound. This rebound is mostly applicable for the heat transfer applications. Okay, where the droplet will come, it will spread, and during that it will take the heat and it will rebound. Okay, so cooling, mostly the heat transfer and cooling applications. So when for the splashing, they are having different applications. So if we increase the Weber number to 80 or 150, you can see the violent splashing is occur, and even for depending upon the Weber number, the splashings are not equal. So different kind of splashings also can be observed. Okay, so now we increase the angle. You can see the 45°. Eventually the dynamics changes, and now we are increasing to 60° for different Weber number. Now you see initially at Weber number 80, the droplet at 30° angle, the droplet was splashing. Now it is not splashing. We'll come into the details why it is happening, but mostly if you increase the angle, eventually your mg sin theta component, that is which is giving you the extra tangential momentum to the droplet, eventually that force is somehow adjusting the effect of the impact velocity or the impact momentum, and it will taking away some impact momentum eventually. So the extra force that causes the splashing eventually is getting reduced, and the dynamics flip from the splashing to the rebound. Okay, so these are the quantitative measurements. So for different Weber number, different angles, you can see, and we have derived a correlation for these maximum spreading parameters in terms of Weber number and the inclination angle. So yeah, so as you can see, if the Weber number is increasing, eventually it is positively the Weber number is in positive power. So if you increase the Weber number, so the spreading will increase. But if you are increasing the inclination, if you are increasing the inclination angle, okay, uh, uh, yeah, so the spreading will decrease. Yeah. So now we have calculated the different, we have calculated the lengths, the leading edge and trailing edge length uh, for different inclination angle and for the different Weber numbers also. Okay. So yeah. So as you can see, as the inclination angle increases, the gravity component increases. As I said, the mg sine theta component, and most of the fluid volume accumulates on the leading edge of the droplet, and hence the leading edge length increases. For the similar reason, trailing edge length also follows the same trend. For a particular inclination angle, if you increase the Weber number, that means the impact velocity, the inertia component along the plane also increases, and hence the leading and trailing both lengths increases. Now coming to the regime plot. So this is very important. So we have characterized the different regimes based on the alpha and Weber number. So here we have listed only three regimes, that is the depositions, rebound, and splash. Okay. Yeah. So now these are the effect of different SCA static contact angles. Okay. And for different Weber number, as you can see, the dynamics is changing when you are changing the static contact angle or the materials, and we carried out the similar kind of studies. I'm not going into the details, but here as just I want to mention one thing. So below 90, if the static contact angle below 90 degree, that means the surface is hydrophilic surface, and if you increase from 90 to 120 degree, it becomes the hydrophobic, and more than 120 degree, it becomes the super hydrophobic surface. So eventually, if your surface is hydrophilic, eventually the droplet spreading will be more and more the surface is becoming the hydrophobic, your the spreading will start to decrease. Okay. So yeah, we performed for different materials, for different angle of inclination, for different Weber number. Okay. So yeah. So as you can see, at angle 30 degree here, there is an important observation that at 30 degree angle, if you run the simulations for Weber number 40, eventually you will see after reaching the maximum spreading, the droplet is splitting up. We are not saying it is very different from splashing. So in splashing, you cannot able to calculate the spreading parameter at all, but here the droplet splitting is taking place. Just the droplet is reaching its maximum, and when it start to recede, eventually it splitted up into the pieces. So that is called the droplet splitting. Okay. Yeah. So okay, now this is the results obtained by the AdaBoost algorithm. That is, from this table you can see we have calculated these parameters. These are the accuracy, precision, recall, or sensitivity, F1 score, and mean square error. Okay. So yeah. So in yeah, and this is the true table. Okay. And that is the TP stands for true positive, FP stands for the false negative, and TN. Okay, so these are the things. These are the self-explanatory. So what is happening? So yeah, in this table, let's say what is happening actually, it is in your in your y-axis, and what our model is predicting, that is in your x-axis. So as you can see in the deposition case, if you see the first row, so mostly for the 12 models, it is predicting exactly deposition. But for two cases, actual is deposition, but our model is predicting the rebound. And for the rebound cases, yeah. So for 15 models, our our for the 15 cases, the model exactly matches. But for one cases, actual is rebound, but our model is predicting deposition. This one. And for splash also, you can see it exactly matches for 12 cases, but in one cases, our model says rebound, but that was actually splash. So in this way, you can check the accuracy of your machine learning models. For different models, these numbers will change. This number will be different. Now, coming to the conclusion, at lower inclination angle, at lower inclination angle, the Weber number uh, the lower SCA, the results in the greatest spreading factor due to the hydrophilic nature of the surface, as we already mentioned. And as the SCA increases beyond 90 degrees, the surface becomes progressively more hydrophobic, and beyond 120 degrees, it turns to be super hydrophobic, leading to decrease in the spreading factor. At a higher Weber number, the partial splashing was observed, that we are saying the droplet splitting across all SCs up to the inclination angle of 30 degree. When the inclination angle reaches 45 degrees, the droplet dynamic shifts from the splashing to rebound due to the increased axial momentum transfer caused by the higher inclination. And a classification-based machine learning algorithm, AdaBoost, was developed to predict the droplet dynamics based on the CFD simulation results. This algorithm achieved up to 90% accuracy in predicting the droplet behavior on inclined surface, with potential for improved accuracy for the larger data set. Now coming to the case study 2, that is the numerical simulation of post-impact dynamics on a droplet on a moving surface. So so previously we discussed in brief that up to the author's knowledge, there are very few literature available on the droplet impingement on a moving plane, and most of the studies are experimental in nature, where there is a scarcity in the numerical studies. So there is no comprehensive study available which explain the effect of impact velocity on the droplet, tangential velocity of the plane, surface wettability, and the droplet size altogether. So most of the studies discuss the spreading in axial directions, while the spreading in transverse directions or the lateral direction during the post-impact is also important to consider. So in the present study, what we did, the effect of normal impact velocity of the droplet upon impacting a moving plane is numerically studied. The effect of surface wettability, that means the effect of different static contact angles on the droplet dynamics upon impacting the moving plane, is numerically investigated. The effect of tangential velocity of the plane, okay, on the its post-impact dynamics has been studied, and the effect of the size of the droplet, since the effect of gravity on the post-impact dynamics were studied in a wide range. So this is now your the simulation geometry and the simulation geometry and the boundary conditions. Okay, so this plate is moving. So again, for the simulation setup and the simulation assumptions, as you can see, this case is happening like this, and you see the altogether it is a different dynamics. So here we have used these parameters I have listed here, and we have conducted the validation study, and you can see the validation error. The error in calculating the spreading factor is 4.5 to 5% around, and which is in the permissible range. And from the visualization experiments from Zhang et al., you can see our simulations are in agreement, in a good in agreement with their experiments. Okay, yeah. So now you can see, yeah. So first consider, we are keeping constant. If you see the first row, this first row, we are keeping the tangential velocity constant. That means the tangential Weber number, and we are varying the impact wave number or the impact velocity or the normal velocity of the droplet. So eventually you can see at wave number 40, you can see the splashing. But when we are increasing now from here to here, when we are increasing the tangential velocity from 0.5 meter per second to 1.5 meter per second, but keeping all the normal velocity or the impact velocity same, you can see at the wave number 40, it is no longer splashing. The dynamics become change from splashing to rebound. This is because of this tangential motion of the plane is imparting a tangential momentum to the droplet, and that is somehow uh, adjusting the impact momentum that causes the droplet to splash. Okay, and these are the quantitative visualization of the data, as you can see. Okay, yeah. So when we are increasing the impact, as I said, for the lower tangential velocity of the plane, if we are increasing the impact velocity, eventually the droplet start to splash after reaching its maximum spreads. But when we are increasing the surface velocity of the plate, eventually you see now the droplet is not splitting or not splashing. Okay. Yeah. So yeah, here we have changed the different we have changed the surface, impacting surface. So that is why the surface contact angle is static contact angle is varying. All of those results are reported for 0.5 meter per second tangential velocity of the surface, and for particularly yeah, so previously it was for impact velocity at impact Weber number at 10, and now it is at impact Weber number of 40. As you can see, at the lower tangential velocity of the surface, eventually the droplet splits up after reaching the maximum. But eventually, at any Weber number, the droplet doesn't show the splashing when the tangential velocity is more. Okay, that is yeah. Now coming to the variation of bond number. So that is what I wanted to discuss, that if your droplet is not spherical, means if your droplet size is larger, eventually your bond number will be larger. So at certain point of time, you cannot neglect the effect of gravity. Eventually the gravity effects come into the picture, and so that is what, if you increase the bond number, yeah, you can see the expression of the bond number here. So yeah, it is the effect of gravity to the surface tension. So if your gravity effect is more, you cannot neglect the bond number. So eventually the gravity plays a role in the post-impact dynamics of the droplet, and that you can see for different tangential velocity and different impact velocity also. Yeah. Okay. So I'm not going into the details. So just coming to concluding for the second case study, that at a lower impacting velocity and at a lower translational velocity of the plane, rebound of the droplet was observed at the same lower translational velocity of the plane. As the impact velocity increases to 40, the partial splashing or splitting was observed. So as the translational velocity of the plane increases, the spreading time of the droplet increases due to the extra, as I said, the extra axial momentum transfer to the droplet at a lower impact velocity. And interestingly, at a higher plate velocity, the droplet with the higher impact velocity, higher plate velocity, the droplet with the higher impact velocity doesn't break due to the suppression of the normal momentum that causes the splashing, basically by the transfer of excessive axial momentum to the droplet by the plate. At a lower SCA, the spreading of the droplet is more due to the hydrophilicity of the surface, and subsequently decreases in the increase in SCA, that means the hydrophobicity increases at the lower Weber number. However, at the higher Weber number, droplet breaks up from SCA of 135 degree onwards. As the size of the droplet is getting lesser, that means the lower bond number, the gravity acting on it is also less, and that decreases the horizontal or the tangential momentum imparted to the droplet, which eventually reduce the spreading and the contact time. However, as the tangential velocity of the plane increases, the additional tangential momentum is transferred to the smaller droplets, which adjust the tangential momentum deficit due to the lower gravity effect, and this eventually causes the increase in contact time of the smaller droplet. Now, coming to the last case study that I will touch upon, that is, so apart from so yeah, so this is our, the previous two case studies were hardcore CFD and some sort of based on those data, some sort of machine learning, um, and you know those VOE based simulations are the grid based techniques, okay, and it depends largely the dynamics depends on the boundary conditions, grids, etc. Now here we are showing a similar case studies, that is the atomistic simulation of post-impact dynamics of a droplet on a moving plane. So yeah, as you can see, the plane is moving, and here the droplet is impacting on it, and in the nanoscale level. And the size of this droplet is around 10 nanometers. This is the nano droplet, and as you know, if you go below the micro level, that means 10 to the power minus 6 meter, right? So millimeter, micrometer. So if you go below micrometer, eventually the continuum hypothesis fails. So you cannot simulate the things based on the traditional Navier-Stokes equations, based on the traditional momentum based approach, or whatever Newtonian mechanics. So for them, we need to do um, the atomistic simulations or the classical molecular dynamic simulations for the and at that scale, this nanoscale level, eventually the interaction between the molecules, interaction between the molecules themselves, interaction between the molecules and the surface becomes very important. And for them there are lots of other models available. So here we have used TIP4P water model. For that, the Coulombic attraction parameters were listed down. So these are not so straightforward. You need to study it. It is very different from CFD, and we did it for different validation cases. Okay, so you can see these are the range of our present uh, uh, the present range, that is the tangential Weber number is from 100 to 300 300 tangential Weber number at a particular impacting Weber number of 15. Okay, and for the validation purpose we kept this at 7.41, this impacting Weber number. And so here you need to, during the simulations, you need to list down all the energy parameters, interaction parameters, or the energy parameters that are available in the literature for a particular model. Okay, and we have varied the different speeds, the tangential velocity. Okay, and we calculated the spreading parameter in x direction, and the maximum spreading parameter in x direction, and maximum spreading parameter in y directions. And we observed something interesting, that is the some hole formation or the gap formation occurs while the droplet is spreading in certain cases. And yeah, so we listed down those time step gaps and the contact time. Yeah, as you can see, so basically these are the particle based methods, and here we have taken the 5,000 particles, and every time, depending on the energy state, these particles are just leaving the surface because of the energy mismatch, and that is very common in the molecular dynamic simulations. So this is the validation. So as you know, in this scale, normally experiments are not available. Okay, so sometimes people validate molecular level simulations with experiments uh, by incorporating uh, some correction factors. Okay, so here we have validated our model with the Zhang et al. 2022 model, and you can see our results are in good in agreement with them. And then we performed the similar studies, that is the that what we did for the CFD, that is the droplet impingement on the moving surface. Eventually you can see this is the beta x, that is your axial spreading parameter, and this is your the lateral spreading parameter over um, different different tangential velocities. And here we have kept the impacting Weber number at um uh, probably 15. Okay, we are not changing the impacting Weber number, rather we are changing the surface velocity, and we got this kind of dynamics. So here I have not listed the conclusion because the study is ongoing. So it is not good to show wrong results. But I wanted to give an overall view. That's why I have included this. Apart from CFD, in the industry, we also do this molecular level simulations, because these are important mainly in the semiconductor processing industries, or where we need to see what is going on at the molecular level. And mostly in the computational material science, these kind of studies are very important to see the how a particular type of droplet is interacting with a particular surface of particular surface, kind of, if this water droplet is impacting on the graphene surface, or it is impacting on the copper surface, or it is impacting on the aluminum surface, whatever, the surface interaction parameters will change, and eventually that will change your dynamics, and eventually your outcome will change. And sometimes it is very important to see the corrosion in the materials. So for those kind of studies, this molecular dynamics is very useful. So thank you.
Yes, sir.
Any question?
If any participant is having questions to Mr. Arnab, sir, you can ask him in the chat box or unmute yourself as well.
There are some questions in the chat box.
Okay, I can see only one question. Yeah, so what is the question? Can you please tell which solver was? Yeah, so solver is already mentioned in the PPT. Oh, how do you decide which solver to use, simple or piezo? Yeah, so you cannot decide based on that. So, okay, we conducted, you need to conduct some cases and see which solver is giving you what kind of results. So, as you can see here, so yeah, run the same simulation using piezo and simple, and you see what is the difference in error, and compare that with your some standard cases that people have already reported. And if you see the error is less, like is insignificant, then yeah, the simple is more convenient to use than piezo due to the convergent issues and all.
Hello.
Yes, hello.
So my question is that how you select the appropriate data set for their machine learning model, and what are the
data set.
criteria you have selected for this number data set is perfect for this, or while performing this machine learning model to integrate that?
Yeah, data set, see, for machine learning model, as you know, so we are having some plan to do pins also. So the thing is, for these machine learning models, you know, you need to have a larger data set, right? So first we conducted all the CFD simulations. Let's say lots of CFD simulations. Here I have shown you very specific cases. So once you acquire the data, then only you can do machine learning. Otherwise, there is no point in doing machine learning, right? Because you need to train your model. For that, you need to spend 20% of the data. Let's say we used 2080 kind of thing. So you need to train your model for the 20% of data, and then you need to predict it. So eventually you need to have a very high volume of data set, whether it is experimental, whether it is simulations. But yeah, first you need to conduct the simulations. Otherwise, you cannot do the machine learning. That answers your question?
Yes, yes. And second, my question is that by selecting the data set, you have to be selected the simulation time steps. So some information in between is lost if you taking the larger time step simulation data to tuning the machine learning models. So how you decided that this data sets and time data
See,
time
first you forget about the machine learning. First, as you know, for the CFD, we usually do two kind of grid convergence. One is the mesh, the spatial convergence, and one is the temporal convergence, right?
Yes, sir, yes.
Yes. So first you focus on the CFD simulation. So you do whatever is required for the CFD, and once the data is accurate, because if you cannot, you are talking about the time step. That's why I'm telling. If you are if your times the if your simulations are not converged in temporally, what will happen? Let's say actual dynamics is something at let's say t is equal to 1 second, but your model is giving something else in the t is equal to 1 second. So first focus on the CFD simulations, the grid, the spatial and the temporal grid resolutions, and once it is done, then you use those parameters in the machine learning model. Otherwise, it won't able to predict, or in fact, after that we used to reconstruct the surfaces, right? So we want to build the similar kind of dynamics, similar kind of images. Those we usually get from the CFD. So you are getting my point. So let's say at certain Weber number you don't have CFD data, but you want to reconstruct the surface. How can you reconstruct? So based on those data, so those data should be accurate. So yeah, so to answering your question, so
Yes, sir. My question is that if your simulation part is accurately, you have validated and you have to done grid independent based studies, these are correct. Then after you have to make decision that how much appropriate data you have to tune data set in terms of the image.
So there are so as you can see there are if you see the literature, so sometimes people tune 25 train the 25% of data set, right? And then predict. Sometimes 20%, it's up to you. So we have used 80-20 model.
Okay.
Now what is the case? First case mention application with deposition and rebound dynamics you can elaborate on the applications where splashing dynamics can be utilized. Yeah, so the splashing, see, splashing is having many applications, like yeah. So in nature, if you see this disease spreading, so if your impact if your impact velocity is very high, eventually for the rebound and etc., you can see it will go deposition, the spreading is very less. If you see the rebound, so in that case also it will go up to the certain length and then it will start to recede. But if it is splashing, eventually the droplet, the part of the droplet volume or the droplet mass can spread here and there, and eventually the risk is more. Okay, this is the one thing. And another splashing application in the nuclear power industry, let's say and in nuclear power, what happens, these sodium droplets, so for the if you there is certain leak and eventually the cooling water or the reactive water usually comes and it hits the some cylindrical pipe surface, right? And it splash because those pipes are hot. So yeah, so depending upon the intensity of splash, it severely affects the heat transfer characteristics as well as uh, creating local cooling. So you know the materials, if suddenly cooling and heating takes place, eventually that affects the material, right? Yeah, and there are other effects also. So um, uh, if you see exclusively this splashing, um, yeah, so for the timing I can remember only these two applications, because mostly my cases generally we focus on the deposition and rebound, and we try to look into the limits where the splash starts, okay, so that we can avoid it. So yeah, so what I can remember, I can say as of now these two applications. So that answered your questions, I think, Soham. And next, how the bond number is significant for the bubble flow. Okay, so as you know, the bubble rise. So I do not work on the bubble flow, so I cannot say it explicitly. I cannot comment on it because it will be wrong if I comment uh, without knowing it. But what I know, what I have seen from simulations, so bubbles rise on the just opposite to the gravity, right? And droplet is always coming due to the gravity. So eventually my assumption is that eventually the dynamics will be the opposite. So for us, we neglect the bond number. For bubble, we cannot neglect the bond number because eventually it is going against the gravity. So it should be it should be simulated in a high bond number. And for bubbly flow, yes, the bond number is every time important, because as you can see that bubbles always grow against the gravity, right? I hope that answer your questions. And what are the experiments and experimental setup? No, we did simulation. We have not done any experiments. So which solver can we simulate? Moving particle. So there are so yeah. So for the moving, no, you are saying about moving particle or moving contact line. So for moving particle, if you're saying the droplet is impacting, no, that can be done in the normal solver. But if you're asking for the moving contact line, then yes, you need to write UDF. So there are lots of models, the Chrysler models and other Zhang models. So there are lots of models nowadays available for the interface tracking. So you need to incorporate them in a separate UDF and patch them up. So you have done the phase change simulation in uploader format. No, we so if you see my assumption slide, I have explicitly mentioned that there is no heat transfer. So we are having a plan of doing it in future, because our applications were mostly on the tablet coding, 3D printing, those kind of stuff. So there the heat transfer was insignificant. What are the most significant open challenges understanding multi-phase flow and tablet in the current measure still struggle with? Yeah, triple phase contact line. But because if it is an evaporation case or condensation case, or the surface is moving, if the surface is even rotating, every time that the behavior changes. So the DCA models, dynamic contact angle models, that is a big challenge. And can we verify this? Yes. So many people did experiments. So you can see sometimes we verified with Sao et al. Professor Purbalantha's group at that point of time. It was in IIT Ropar and now it is in IIT Kharagpur. So they did extensive experiments. So yes, those results can be verified using experiments. But for us, we did not have the experimental facility, so we need to rely on the literature, what other people did experimentally, and that is what the simulation guys do. If a droplet is formed in a supersonic gas flow, very good question. The pressure and temperature drop with multi-phase solver model. I don't know. I need to check it, because I have seen these kind of experiments in my present lab, that droplet shock interactions. Yeah, is very similar to your question, but in simulation I need to check for which kind of model we can use. So I hope we have answered all questions.
Hello.
Yes.
Yes, sir. Sir, my question is your last part of study, which you have done nanoscales bubble formation.
Yes, those simulations are still going on. Please ask. Yeah, you can ask.
Yes, sir. You have to consider the particle-based model for that formation of bubbles. During this, you have to consider some forces and particle-particle restitution coefficient and particle-particle interaction is taking place.
Yes.
How you taken that parameter? How these are
Oh,
very
those, yeah, that is a very important question. The thing is, for the at least we have started this kind of simulations.
yes.
So what I can say is, yeah, it is very difficult to simulate for the unknown things. So we started for those kind of liquid and surface. Those the datas are available in the literature, in the previous literature. So later we will think how to simulate the unknown things, but as of now, I don't have much idea on that.
Okay, sure.
Yeah. We stay in touch probably in the next session whenever I'll give a talk. I can make an explicit and exclusive presentation on this. Okay.
Yes.
Yeah, because unless you are studying the things very rigorously or in a detail, it is not good to uh, answer based on your assumptions, right? Any further questions?
No, sir. No, sir.
Hello, Payal.
Yes, yes. I can see that, I think all the questions you have answered on the chat box also, and those who have asked through your audio also. So thanks a lot. Thanks a lot, Mr. Arnav. So you have been very patient in, answering all the questions, and your presentation was also so informative. It was so detailed. I hope all the participants have been, it has been very effective for all the participants. Yes. So I was saying that Mr. Arnav Chakraborty is one of the esteemed member of the advisory board of the CFD team of FOSSEE, and he is from TCS Research and Innovation, TCS Innovation Lab. And it has been very, he has been very generous, and we are very thankful to him for this session. Thanks.